Okay, now we will study how to compute the inverse of a matrix. So the very first method is called the Gauss-Jordan method. So suppose that we have a matrix A, which is square matrix and whose inverse exists. Since I told you that there are some matrices whose inverse exists and there are some matrices whose inverse doesn't exist. The matrices whose inverse exists are called non-singular, and those matrices whose inverse do not exist are called singular matrix. So if A is a square matrix whose inverse exists, so there is an algorithm to find the inverse of A. So that method is called the Gauss-Jordan method. So what is the Gauss-Jordan method? Now I will explain it. So the very first step is to form an augmented matrix A with In. Since A is a matrix of order n, so therefore I have augmented this matrix with identity of order n. So the next step is to perform raw operations. When I will apply raw operations, my A will be converted into 1 1 1 in the diagonal and everything else is 0. That means I will get identity, and here the thing in the thing here in the place of B is the inverse of A, and this B is obtained after applying raw operations. And you can see that identity is transferred here on the right side. The last step is just call B is equal to A inverse. So let's do an example. In this example, we have to find the inverse of this matrix. So the first step is to form an augmented matrix A augment with I. So I will first form this augmented matrix. First I will put A, then I will put I. Now I have to perform raw operations to make this matrix identity, and this matrix will become anything else. Here we have 1. I have to make this 0. So how can I make this 0? If I write 3 minus 3 times 1, this means R2 minus 3 times R1. So this operation I will perform in row 2 to make changes in R2. So 1 2 1 0. So 3 minus 3 times 1, 4 minus 3 times 2, 0 minus 3 times 1, 1 minus 3 times 0. This is the operation. Let's simplify this. 0, 4 this is minus 2, and this is minus 3, and this is 1. Now we have to make here 1. How can I make this 1? If I divide R2 by minus 2, and this is my new R2, then it can be 1. 1 2 1 0 0, and this is 1, this is 3 by 2, this is 1 by 2. Okay, sorry, I am going to divide by minus 1 by 2, minus divided by 2. So therefore this will become minus 1 by 2. Okay, Now I have to make this 0, but I will use this. So it can be 2 minus 2 times 1. In other words, this 2 is R1 minus 2 and this is R2. So I have to perform this operation here, R1 minus 2 times R2. But this operation will be performed in R1. So 1 minus 2 times 0, 2 minus 2 times 1, 1 minus 2 times 3 half, 0 minus 2 times minus 1 half, 0, 1, 3 half minus 1 half. Now simplify these calculations. 1, 0, 0, 1, and here I have minus 2, here I have plus 1, and here I have 3 half, here I have negative 1 half. Now you can check that this is identity and this is your matrix B, and this B is the inverse of A. So I can say that inverse of A is negative 2, 1, 3 half and negative 1 half. Okay, this is the inverse. Let's do another example. Okay, let's do a theorem here. But before going to the theorem, let's check here. So if you are given a matrix and you are going to find its inverse, you have to perform raw operations to make here identity matrix. Suppose you are given a matrix and you are performing raw operations and you are not getting identity here at the end. Here you are not getting identity. That means here is the pivot entry, this is the pivot entry, there can be more pivot entries. If you see that there is some 0 in the pivot entry, then we will say that this matrix has no 1 1 on the main diagonal, and this matrix is not good matrix, and we will say that this matrix is singular and it cannot have inverse. So the theorem is the same thing. Theorem will say that a square matrix is invertible if and only if its reduced echelon form is identity matrix. What does that mean? If you convert it into row reduced echelon form, it will give you identity. If it is not giving you identity, that means it is not invertible. This is what theorem says. And there are other points are written in this slide number 8. We have to perform Gauss elimination method. If any pivot non-zero entry, if every pivot entry is non-zero, then it is identity, so it is invertible. If any pivot entry becomes 0, that means it cannot be inverted. By pivot entry, I mean these entries, the diagonal entries. It says if all of the diagonal entries are non-zero, that means I can convert it into echelon form and it will be converted into identity. If any of these entries becomes 0, that means this is no longer going to an identity matrix, so that means it cannot be inverted, so it is singular matrix. So I'm not going to write the statement of the theorem. Now I can solve an example. So the example on the next slide is, you have given a matrix A 1 1 1 0 1 3 2 0 A. So in this example we will find the value of A for which the matrix is non-singular. Okay, we have to find the value of A for which the matrix is non-singular. Non-singular means all the pivot entries are non-zero. If any pivot entry is 0, then it is singular. So how to prove that this is non-singular? We have to convert this matrix into row reduced echelon form. Okay, so 1 0 2. So first of all, I will make here 0. How can I make this 0? If I do this operation r2 minus r1. Okay, so I am doing this 1 minus 1, 1 minus 0, 0 minus 2. So this is r2 minus r1. Also I want to make this 0, that means r3 minus r1. So let's do r3 minus r1. 1 minus 1, 3 minus 0, a minus 2, r3 minus r1. So this is 1 0 2, 0 1 minus 2, 0 3, a minus 2. Now this is pivot entry and this is 0. This is pivot entry, this is 0. Now I have to make this 0. How can I make this 0? I can make this 3 minus 3 times 1. In other words, r3 minus 3 times r2. So this operation I will perform, r3 minus 3r2. How? Let's check. 1 0 2, 0 1 minus 2, 0 minus 3 times 0, 3 minus 3 times 1, and a minus 2 minus 3 times minus 2. You can check. I have performed this operation here. Okay, r3 means 0 3 a minus 2, 0 3 a minus 2, and minus 3 is everywhere, you can check, and r2 is 0 1 minus 2, you can check, 0 1 minus 2. So this operation is okay. 1 0 2, 0 1 minus 2, 0 0, and a plus 4. This is non-zero, this is non-zero, this should be non-zero, because if this pivot entry becomes 0, then this matrix is not good. I will say that this matrix is singular. I want to make this matrix non-singular. I have to find the value for A for which the matrix is non-singular. So non-singular can be only when this is not equal to 0. So A is non-singular if and only if A plus 4 is not 0. And what does that mean? A plus 4 is not 0 means A is not equal to minus 4. Okay, and this is the value of A. So for all values of A except 4, this matrix is non-singular. So the next definition is the definition of Cramer system. So the Cramer system is a system of equations whose coefficient matrix A is non-singular. In other words, whose coefficient matrix A is non-singular. Non-singular means it is invertible. A is invertible means it has inverse. When it will be non-singular, that means it will have inverse. In other words, the determinant of A is not 0. I told you that if the determinant of the matrix is non-zero, then still the matrix is non-singular. So there are two conditions for the matrix to be non-singular. There are two conditions here. A is non-singular. Non-singular means invertible. And you know what invertible means? Invertible means whose inverse exists. Either A is identity after row reduced echelon form. I mean, if I apply row operations on A to convert it into row reduced echelon form, it becomes identity. In other words, all pivot entries are 1 1. Or the determinant of A is non-zero. If any condition holds, then we say that the matrix is non-singular. Sometimes we will check that A is identity in the row reduced echelon form, and sometimes we will check that the determinant of A is non-zero. So both conditions are interchangeable. Okay? So we say that the system is Cramer system. The system is Cramer system when the determinant of A is non-zero. Okay, here is an example. The given system minus 5x plus 2y is 3a, 3x minus y is 2b. We have to check it is Cramer system. We have to check it is Cramer system or not. We have to check. So what is the coefficient matrix here? The coefficient matrix A is minus 5 to 3 minus 1. So I have to check the determinant of A. The determinant of A is negative 5 times negative 1, multiply these two, and then minus multiply these two. So this is 5 minus 6, which is minus 1. Since the non-zero determinant implies the system is Cramer system, since this determinant is non-zero, so the system is Cramer system. So the system is Cramer's system.